So let's come to the next talk. It's a pleasure for me to announce this. So Roger Dendaldine will talk about HOP. We'll talk about the... So, once again, Roger will talk about the Tor project. He is the project leader of Tor, and I'm pretty sure most of you have tried Tor already and might have recognized it's sometimes a little bit slow. And Roger will talk about this now. Thanks a lot.
Okay, hi everybody. I'm Roger Dingledine, the project leader for Tor, and today we're going to talk a little bit about problems that we've encountered when trying to build Tor and make it scale better. Can you all hear me just fine? Great. Okay, so there are a lot of things we could talk about. I'm going to give you a very brief crash course on how Tor works and who uses it, and then we're going to get into the performance issues and architecture problems and so on. So Tor is free software, open source, unencumbered. It comes with a specification and full documentation, RFC style, that describes here's exactly how you can build your own compatible Tor client. And a number of people out there have done that. There's a group in Dresden that built their own Tor client, and another one in Aachen, and a fellow at Yale University built his own. And part of the fun of this is that we actually can describe all the details of what properties we think that Tor gives you. So you can look at it and check for yourself and analyze it, and we tell you as much as we know about how it works. There are about 1,800 volunteer relays all around the world routing traffic for some number of users. It's an anonymity network, so it's a bit hard to tell how many for sure. But I'm figuring more than 100,000, less than 500,000 people are running Tor clients right now. As of the end of 2006, we became a real live 501c3 US nonprofit. We've got 8 full-time people working on developing Tor right now, which is pretty cool. So we started out funded by the Naval Research Lab, part of the US Department of Defense. And from there we were funded by the Electronic Frontier Foundation. So our claim to fame is that we're the only free software project funded both by the US DoD and the EFF. And from there we've been funded by Google and a variety of other organizations that care about privacy and freedom around the world, and by NLNet, and perhaps by some people you know. Feel free to get them in touch with me if you know anybody around the world who wants the world to be a safer place. So what do I mean by that? I actually only use the word anonymity when I'm talking to other researchers. When I'm talking to my parents and my grandparents, I tell them I'm working on a privacy system. When I'm talking to Google and Walmart and other companies, I tell them I'm working on communication security or network security. Because anonymity, that's kind of scary, and privacy, who cares about that? But security, good point, I do need that. And when I'm talking to law enforcement and other government groups, I work on traffic analysis resistant communication networks. Because security, they've already got that. There are plenty of snake oil companies around the Capitol that are happy to sell security products. Who cares if they work? Who cares if they work? And privacy, whatever. Anonymity, okay. But traffic analysis resistance, that's a good point. I really do need that. I want to be able to send my operatives to Israel and not have anybody learn which countries they're talking to. Or I want to be able to investigate this website that some bad people are running without revealing that I'm the one doing it. And then there's a fourth category that we've been learning about recently, which is the reachability side, the blocked users, people in Iran or China or Thailand, or the list goes on and on these days of different countries that are blocking various pieces of the internet. And there are a lot of people, it turns out, once you've built an anonymity system where somebody watching you locally can't figure out which websites you're going to, then that also means that a government locally can't decide which websites you're allowed to reach. It can't block you from getting to CNN because it has no idea which sites you're going to. But that's a separate talk, and you might be able to learn more about that this year in Berlin in December, and in 2 hours there will be a WikiLeaks panel discussing censorship. So how do you build one of these? The very easy answer is you put a computer somewhere and everybody relays through it. We call it a one-hop proxy. And so Alice 1 asks for some website, and Alice 2 asks for some other website. And that's great, except what happens if there's a central point of failure. That big point in the middle, you can break into the colo and steal the computer. You can put a guy named Guido on an airplane. You can send a subpoena legally or illegally. There's so many different ways to attack a single point of failure. So the goal for Tor is to distribute the trust over multiple hops, so no single relay gets to learn both Alice and Bob. And that means if the first guy is bad, if R1 is trying to figure out what's going on, he can learn that Alice is using Tor, but he doesn't know what she's doing. And if the third one is bad, he knows that somebody is talking to Bob, but he doesn't know who is talking to Bob. And if R1 and R3 collaborate and try to figure it out, then we're screwed. We can't provide everything. But at least it provides a stronger level of security than just the single hop proxy. So far, so good? Okay. And there's crypto, but I'm not going to talk about that today. So we have been trying to figure out what parts of Tor are slow these days. And here's a graph, courtesy Karsten, so we downloaded a 50 kilobyte file 14,000 times over Tor. And we tried to figure out how long it took each time. And there are a couple of things to point out here. One of them is the median download time. The average time that it takes to fetch the 50 kilobyte file is almost 8 seconds. So I want to download a website. It takes something like 8 seconds for me to actually get the website. So that's the first thing to notice. The second thing to notice is this huge long tail here that there are so many of those connections that take 20 seconds, 30 seconds, something like that. So it's really the variance, the variability of the latency that's a big problem. So let's look at that a little bit differently. So here we're looking at downloading 50 kilobytes or 1 megabyte or 5 megabytes. So the previous graph is this little blotch down here where we have an average of 8 seconds and the first quartile and the third quartile. But when we're looking at the 1 megabyte one, it takes 50 seconds or something on average to fetch a megabyte through Tor. It's not so bad. And then when we're looking up here, 5 megabytes takes 150 seconds to fetch 5 megabytes through Tor. So we've actually got a couple of problems here. First of all, fetching small files through Tor takes too long. Second of all, fetching large files through Tor is surprisingly fast. This is not what we built this thing for. And there are a lot of people using it for bulk transfer at this point, and we'll get to that in a few more slides. So there are a bunch of things that we need to talk about in order to figure out how to fix it. And I've identified 6 main categories here of problems that we need to work on. And I'll walk you through each of them as we get to them. And they're ordered by priority. So if we solve only number 3, 4, and 5, and we don't solve 1 and 2, then we're not really going to see the results of fixing those. So we need to solve the first few in order to be able to solve the rest of them well. Okay, so the first one. Congestion control and flow control aren't really done the way that they should be. So Tor uses TCP between each hop when it's connecting. So you use TCP from Alice to the first hop, TCP from the first hop to the second hop, and so on. And that means that there's one TCP connection between 2 Tor relays. And we multiplex a lot of the circuits, a lot of the connections through that TCP stream when we're connecting from one relay to another. And TCP really wasn't designed for that sort of thing. It's only got one trick when it wants to slow you down. And that trick is, I drop a packet and hopefully your window goes down and then you'll start sending less stuff. So the other way to look at that is if one of those connections is sending too much traffic, then all of them get punished for being too fast and it's going to slow all of them down. So we need to figure out how to break that up so that we don't have one TCP stream sending all of them, but we have a whole lot of different streams. And the first answer is, well, then just have one TCP stream for each connection that's going through. And that turns out to break all of the cable modems out there because they can't handle that many connections in their state table. So the easy fix, I say easy, but turns out to be complex in practice, is that we need to switch from TCP to some sort of datagram, some sort of UDP-based protocol. And the first step was, let's switch to UDP on the network, and let's put user space TCP proxies on the first edge on Alice's side, and then another one on the far side. And they need to be user space, because otherwise you're going to be leaking details about what OS you are and stuff like that by the characteristics of the IP packets that you're seeing. So that's great, except there are no usable, secure, maintainable, portable, free software and a few other properties, TCP stacks out there. And we've got a professor named Ian Goldberg who's working on this problem at Waterloo, and he has a series of master's students who are looking into it. The latest idea is that we should do user space SCTP, and I'd be happy to chat more about that one later. It's a big, complex mess. Every time I talk to different systems people, they say, oh, you should do it exactly like this, and those other ideas are all horrible, except they're all pointing to different ideas whenever they say that. So I really have no idea which way we should go next. And I've been talking to other folks who suggest that you don't want drop-based congestion control. You don't want a system where if it's talking too fast, you drop a packet. Instead, you want to be doing delay-based congestion control, where you see how long it takes for the packet to get from one end to the other and back. And then you can do the math and figure out how much you should slow down or speed up. Okay, so another problem with the congestion control, flow control stuff. Right now, we've got built-in congestion control end-to-end in the Tor network. And the way it works is, as soon as I build my circuit, as soon as I make my connection to the other end, and I ask for CNN or some website, there's a circuit window that specifies how many cells that exit node is allowed to send back to me. And it starts out at 1,000. So that's half a megabyte of stuff that it's allowed to send. And once it's sent that half megabyte, it's not allowed to send any more until I send some acknowledgement cells to it saying, okay, I got those, now you can send me more. And that's a great idea in theory, except first of all, it's a fixed size window. It's not dynamic like TCP. And second of all, it's huge. 1,000 cells is way more than most windows are going to be. And back at the beginning, I was thinking to myself, okay, so my goal is to maximize the throughput that we can get through Tor, and obviously that means that we'll optimize all of the other network properties like latency and all sorts of other stuff. And that turned out to be a reasonable assumption when we had 1,000 relays and 50,000 users, and it turned out to be a really poor assumption when we're up to 2,000 relays and many hundreds of thousands of users. So we need to cut down that window size. Keeping it fixed doesn't seem so bad, but if we cut it down to 100 cells, so you can only fetch 50 kilobytes at a time before you have to ask for another batch of cells, then we're going to be providing better service for the people who aren't fetching very much and slowing down the people who are fetching a lot, and then hopefully there will be a better balance. Okay, so those were a couple of problems that we need to talk about in the first issue. The next one is, let's think more about this bulk transfer. How does that work, and what can we do about it? So the first thought is, economics can tell us a lot about this stuff. Once upon a time, we were thinking there's going to be an equilibrium. If the Tor network is really fast, we're going to attract more users, and it'll slow down again. And if it becomes slow, then some of the users will give up and leave, and it will speed up again. So we imagined this point, this optimal latency of how many users we're going to have. The problem there is that different types of users have different tolerance for latency. So while the web browsing users, while the people in Iran who are trying to get to Twitter are clicking and wondering why it doesn't work, there are people elsewhere who are setting up their BitTorrent file and then going to sleep. So the people who are sleeping really don't care if the latency is 7 seconds or 9 seconds or 4 seconds, whereas the people who are trying to web browse really care about that. So how can we balance this? The way that Tor does its round robining right now, so at the Tor relay, there are a bunch of different circuits that all have cells that they want to send right now. Right now we do round robin. We just go one at a time and say, whichever circuit has something that it wants to send, you get to send one cell. And that means that if the relays are all rate limiting a lot, then the people who always have a cell that they want to send, the circuits that always have a cell they want to send, are going to end up sending a lot more cells over the course of that second. So if I'm rate limiting to 50 kilobytes a second, then the BitTorrent people are going to use up 47 of that 50, and then the web browsing people get a little bit in. And that's not good. That's not fair. We started out thinking that round robining through all of them was the correct way to do fairness. So the next step is, how do we become less fair or more fair? So here's a graph of all the circuits that 9 or so relays have seen over their lifetime. And we've ordered the circuits by the loudest 10% over here to the quietest 10% over here. And what we're looking at is the number of cells that they've seen over the lifetime of that circuit. So the really fast circuits, the really loud circuits, the ones that have seen the most cells, are seeing 2,000, 3,000, 5,000 cells. So that's several megabytes of data. And then if we look at just 10% over, the 20 percentile most loud circuits, they're only sending a few hundred cells. So there's really 10% or less of the circuits are really, really loud, and the rest of them are really not that loud. And if we look at it in terms of what's going on in the buffers right now, how many cells are queued on average for each circuit, the loudest 10% of the circuits, they've got a bunch of stuff queued. They've always got a kilobyte or 2 kilobytes or 5 kilobytes or 10 kilobytes of stuff queued waiting to be sent out. And the rest of them have nothing. So 90% of the Tor circuits are very quiet and very polite, and they're doing just fine. And a small percentage of them are sending most of the traffic, and they always have something more that they want to send. So what we need to do is, when we're doing that round robining, we need to weight it by how loud the circuit has been lately. So if you keep on sending cells, then you don't get to send the next cell. You get downgraded, and the people who haven't sent much lately get to send the next cell. So that's a great intuition, but what do we actually do? How do we pick the algorithm? How do we decide if it's going to work? A fine question. I'll let you know in a few months once we figured it out. If you've got any ideas, please let me know. The basic idea that we're heading towards is some sort of weighted mean, where we look at the number of cells you've sent recently, exponentially falling off by how long ago you did, and we choose more likely the ones who have a lower mean number of cells they've sent lately. Okay, another thing we can ponder, maybe we should be throttling the bandwidth in the client. If we've got all these file sharing people, all these bulk transfer people, maybe we should say your Tor client can send 20 kilobytes a second. That's all you get. And on the one hand, it's not really a very stable solution, because some guy is going to build a Tor++ client that doesn't rate limit itself, and they'll put that out there, and then we'll be competing with that. We can't really do it at the relay. So the next idea is, okay, you can't do it at the client. Let's make the relay rate limit you. But that doesn't work, because there are 1,800 relays. And if I get 25 kilobytes a second times 1,800 relays, then I'm doing just fine. So maybe it's an okay idea. Maybe the Windows users don't know how to change their software, so they'd never fix it. Another reason why it might be a good idea, there are a lot of attacks these days that people are still researching. We don't know how well they work. But the idea is, if you have a sustained flow that's really loud for a really long time, then it makes me easier to track you down and figure out where on the network you are. So maybe we'd actually be making you safer against some of these new anonymity attacks if we make sure that you can't talk really loudly, really consistently for a whole 10-minute period or something like that. Okay, so those are the first two. Then the next idea is, we need more capacity. We need more relays. You guys should run some relays. And a lot of people that I talk to are thinking, well, capacity is obviously the #1 problem. If we just get you more relays, then Tor will be faster. And it's true, if we get more relays, Tor will be faster. But if we don't solve the first two, then getting more relays is not going to help us as much as it should. If we don't solve the fact that we do congestion control wrong, and we don't solve the fact that the bulk transfer users are just going to fill up whatever capacity we get, then it's not actually going to make Tor faster for the web browsers. So what can we learn from this? We actually have a little lesson that we can learn from the Iran thing in June, where we see, so this is a map of the number of relays we've had over time, from 2006 up to a spike in beginning of 2008, and then a drop off, and then a huge spike in the middle of June 2009, when a lot of people said, hey, I have to help all those people in Iran actually be able to get their word out, and we can make Tor faster if we run more relays, so let's set them up and find out. So does it actually make Tor faster when you get more relays? So here's the same map of the number of the latency of fetching this 50 kilobyte file over time from June 10 to the end of June. And it actually, the latency starts out around 10 seconds, and then it ends up around 7 seconds. So actually, yeah, Tor does get faster if you add more capacity. And now we're looking at the same thing for the 1 megabyte file, where it starts up here at 70 seconds or something, and it goes down to 50 seconds. So maybe it is a really worthwhile thing to do to add more relays. Originally, we were looking at the economics argument and saying, no, if we add more relays, then the file sharers will just fill them and then it won't get any faster. But actually, it does get faster, both for the file sharers and for the 50 kilobyte people, and for the web browsers. So that's certainly a worthwhile thing to do. I'd really like to solve all three. I'd like to solve the congestion control problem and the unfairness problem, or the fairness problem, and the capacity problem. And then, so there are a bunch of other pieces to how do we get more capacity. We've been doing a lot of advocacy. Jake and I keep going to random places all around the world and saying, let me teach you about Tor, let me teach you how to blog safely, let me teach you how to stay out of jail while still changing the part of your world that you want to change. Should we set up mailing lists just for the operators so they can talk to each other about, I'm getting DDoSed, I got a visit from the law enforcement people, I found this nice guy at the FBI and I started talking to him about Tor, whatever they have to say to each other. We've also been setting up an easy website script called Tor Weather, where you go to the website and you add in your email address and the hash of your relay. And when your relay goes down, it'll send you mail and say, hey, it's down. Because we get a lot of people who happily sign up Tor relays and they're all helping out, except their computer rebooted a day after they set it up, and Tor didn't actually start up and they have no idea. So they think they're being helpful, but turns out they're not. So if we could provide better ways to give them feedback, then we'd be in a lot better shape of having more capacity. So there's another thing to look at here, which is what countries are providing a lot of the relays? Where is this capacity coming from? And here's the same graph we saw a few slides ago, broken down by which countries we're looking at. So Germany was the one that spiked at the beginning of 2008, and then over the last year and a half, it sort of fell off, especially throughout 2008. Is that because all of you guys are scared of the data retention laws and you don't know what they mean? Yes, no, I hear in the audience. Certainly that's worth discussing more. So another thing to point out, the US was basically where all of the nodes showed up in the middle of June. So it was basically a lot of people in the US who were thinking to themselves, I really want to go help out with people. And then another data point to look at, France really jumped up in the early part of 2009 due to their fine Hadopi laws, the 3 strikes from the recording industry and you're off the internet for a year, caused a lot of people in France to say, well, wait a minute, what the heck? I thought my government was a reasonable free country. So there are a bunch of different things that we can learn about how the Tor network grows and how to encourage it to grow. And another thing to think about for capacity, incentive mechanisms. Wouldn't it be great if we could design something into Tor where the more relaying you provide, the faster Tor is for you. So if you set up a relay, then suddenly you can get your web pages or your MP3s or whatever faster than you could before. And there are a couple of problems with this. The first idea we had was a simple gold star design. So the idea is the directory authorities measure your relay and see if you're actually providing performance. And if you are, then you get a little gold star in the directory. And anybody who has a gold star gets priority. They get preferred service from all the other relays. And we did some simulations of this, and it actually works great. The people with the gold stars get pretty consistent service no matter how many BitTorrent users we add into the network. So that's exactly what we want. There's another approach to this based on micropayments, digital cash. The idea is all the people who run a relay are given coins, eCash, and if you run a relay and somebody connects to you, then they pay you a coin to build a fast circuit, and that means that it's just like an economy. It'll work great. You can collect money by being a relay. You can pay money in order to get faster Tor. There's one problem with both of these ideas. If there's a big list of all the people who deserve better service, and I see you connecting to my website and you have fast service, then I go take a snapshot of the list of relays that are up right then. And I say, I don't know who you are, you're anonymous, but you're one of these 1,800 people. Next week, you come back to my website and you log in again. I take another snapshot of the list of relays at the time. I don't know who you are, but you're one of the intersection of this group of people and this group of people. And if this keeps happening over time, maybe that set shrinks down to 4 people. We don't have a good handle on how quickly that set would shrink down, but that makes me really uncomfortable. And intersection attacks show up all over the place in anonymity research. They never have any good answers. So it would be really great if we could come up with some way to reward people by providing relays. But on the other hand, if we're presenting, here's the list of the people who are getting fast service, there are some really bad anonymity attacks there also. So maybe we'll solve those and we'll be able to provide some sort of tit-for-tat design. Why don't we just make you a relay by default? We've got, what, 200,000, 300,000 clients and 1,800 relays. And the way that you become a relay is you download the client and then you click, I want to be a relay. Shouldn't that just happen automatically? Shouldn't everybody who signs up for Tor be a relay? There are 2 sort of categories of problems with that. The first one are basic engineering stuff. I want to be able to figure out if you're actually reachable. Maybe we need to do something with your NAT. Maybe we need to do UPnP. More and more NATs are turning off UPnP. We want to figure out how much bandwidth you've got. We want to figure out if you're reachable. If you stay reachable over the course of several weeks, then maybe you're worthwhile to turn on. Those are just engineering problems. They're hard, but we can do those. Then there's the anonymity problem that I don't have a good handle on. So there are a bunch of attacks these days under the general category called congestion attacks, where if I get to relay traffic through you, then I can figure out, I can do better attacks against you. So the basic idea is, let's imagine you're connecting to some website and you're sending traffic back and forth a lot. If I can relay traffic through you, then I just fill up your pipe as much as I can, and I watch to see whether that other connection slows down. If it does slow down, then I was right. It really was you. So I can do this congestion attack to check, to verify that you were the person making that other connection. And if you're not a relay, if I can't relay traffic through you, then it's harder for me to do that congestion attack. It's still an open research question. How bad is this? What are the trade-offs? Where we're heading right now is, well, first of all, yes, the congestion attack does seem to work if you're sending a whole lot of traffic. So maybe we should do that rate limiting thing we were talking about. But second of all, I can just ping flood you if I pick the correct IP address. I don't have to actually send Tor traffic to you and back. I can just knock you off the network and see if this other guy stopped talking. So there are some out-of-band attacks that we don't have a good handle on either. And maybe the result is, well, that sucks that both of those attacks work, but why don't we at least work with what we've got and encourage people to all be relays. We'll find out in the next year or so. Hopefully we'll have a bit more understanding of these congestion attacks and whether we should solve them, whether we can solve them, what the trade-offs are. Okay, so that was the third one. The fourth one, the load balancing isn't right. So the goal for Tor is every relay estimates its own bandwidth and says, I think I can push 100 kilobytes a second, or I think I can push 500 kilobytes a second. And those numbers all get advertised in the directory, and then clients fetch it, and they choose paths. They weight their choices based on how many bytes each relay advertises. So if somebody advertises 500 kilobytes, they're 5 times more likely to be chosen in their path than somebody who advertises 100 kilobytes. And so Mike Perry has been doing some actual measurements to figure out how many bytes you're going to get from each given relay. So he ordered all of the relays by their advertised capacity, and he actually tried to make connections through all of them. And it turns out if you pick nodes from the top 5% of the relays, you're going to get 80 or 90 kilobytes a second. And if you pick from the rest, it falls off pretty quickly. So the first research question is, what should this graph look like? Should it really be flat? Should it sort of look like this but fall off slower? It probably shouldn't look this unbalanced, because at this point there are a lot of people up there in just the first couple of relays that are really fast and the rest of them are really slow. So the first result is self-measuring bandwidth, the way that relays do it right now. They look at what they've seen and they advertise a number. Not so good. It turns out to produce numbers that aren't as balanced as they should. We're not using the bandwidth that we have as efficiently as we should. We also had to cap the numbers that relays are advertising to 10 megabytes a second, because if you show up and you say, I can do a gigabyte per second of traffic, and we believe you, and clients actually start weighting their choices based on that, then you're going to end up seeing 70% of the circuits, because everybody's going to want to use you. Now that we're actively measuring, if we're actually testing every relay to figure out what it actually can provide, then we could. If you can push a gigabyte a second, we could let clients use you. The Tor network would get a lot faster. There would be a lot more traffic going over relays that could handle it. On the other hand, there's a huge anonymity problem there, because if some guy shows up with a gigabyte per second of traffic and we actually send that many clients to him, he's half the Tor network. We've got 1,800 relays, but one huge one over there is taking up half of the bandwidth. That's fast, but not safe. How do we get the right balance? What about one-hop paths? I talk to a lot of people who really want Tor to be fast, and they say, well, I want Tor to be fast for me, and I don't care about that anonymity stuff, so I just want to use one-hop. I just want to go from me to the exit relay and out. And, I mean, won't that be better for everybody? You'll be loading the network less, I'll get more speed. So once upon a time, when our load balancing was all the clients balance over the advertised bandwidth, the main reason for not doing this was you're going to screw up load balancing for everybody else. If clients load balance in different ways, then we're not going to be able to predict where the load will go, and we're not going to be able to build paths that are fast. So now that we're doing the active measurement stuff and we can actually tell which nodes are overloaded, then that's not so much of a problem. One-hop paths are clearly really bad for anonymity, because there's one place, and if the adversary happens to be watching it or running it, then they know Alice and Bob. Another problem, if exits are scarce, let's imagine 90% of the users started doing this. So only about a third of those 1,800 relays are exit relays. They're the people who are willing to connect to websites and stuff like that. So if everybody starts clobbering those, then they're already only about a third of the network. It's not like you can all just start clobbering the exit relays and you'll get faster service. There's only a certain amount of bandwidth that can go around. So my theory, my claim, is Tor is not slow because we're using multiple hops. I mean, the speed of light is kind of slow, but Tor is slow because of all the bytes that are in the buffers queued up at every relay. And we need to figure out that. And at that point, the fact that you're hopping over several hops shouldn't actually hurt you that much. But the real reason why we don't want people doing one-hop exits is we don't want to increase the liability, increase the exposure of the exit nodes. Right now, because of Tor's design, there's no reason to go collect that exit relay. You're never going to learn who Alice is, because there's always more than one hop. That exit relay is never going to be able to learn who Alice is. But if half of the users start using these things as one-hop proxies, then you might as well go find out. Go collect the computer. Maybe you'll get lucky. Maybe Alice was somebody who didn't care much about anonymity. So we don't want to do that to our exit relay operators and make it even more likely that somebody's going to go steal that computer. Okay, what else is there to think about? It's not just the high latency, it's also that long tail that you saw at the beginning. It's the high variability. So one of the problems we have is Tor does rate limiting with a pretty reasonable idea. The problem is, so the way it works is there's a token bucket, which is a basic CS design. The idea is every second we refill the bucket with a certain number of tokens, and each token represents the ability to send 1 byte onto the network. So if we have a token bucket with 30 kilobytes in it, then we're allowed to send 30 kilobytes worth of stuff, but once we've sent that, then we're not allowed to send any more until the next second arrives, and then we put 30 kilobytes more in, and then we can send those. So the problem is that we're refilling the token bucket every second. And that means what happens in practice is at the beginning of every second there's a spike, and then nothing, and then another spike and nothing. So every second, at the beginning of the second, we're sending everything we can send because we've got all this stuff queued up, and then we're silent for the rest of the second. So what happens from this is we end up with these bumps so this is a map of how long it takes to extend your circuit for each hop. So the first hop takes far less than a second, but the second hop, a lot of them are taking exactly 2 seconds, from when we start the request to when we get the answer for that second hop. And the third hop, a lot of them are taking exactly 3 seconds. And the problem for this is all the bytes are moving through the Tor network once a second. So you move, and then at the beginning of the next second, you get to move another hop. At the beginning of the next second, you can move another hop. So we're artificially adding 3 or 4 seconds of latency when we don't need to. And if we could figure out how to fill the token buckets throughout the second in an even way, then the bytes could move forward rather than having to wait and then move on at the beginning of the next second. And there are some trade-offs here because, okay, I probably shouldn't go to that one yet. So there are some trade-offs here because there's IP overhead, TCP overhead, there's this MTU thing, OpenSSL has its TLS record overhead. So we can't just send 2 bytes out over each TCP connection every so often. We need to find some trade-off between sending enough that the overhead is worth it versus really dividing it up throughout the second. And then another thing to ponder, Tor circuit timeouts. So if I'm building a circuit through the Tor network, right now I have a fixed timeout of 60 seconds or something like that. And if I don't finish building the circuit in that 60-second period, then I throw it away. It's never going to finish. So some of these circuits finish building in the first 2 seconds. Some of them take 20 seconds to finish building. If you actually try using a circuit that took 20 seconds to finish building, it's going to suck. It's going to have horrible other properties, latency properties, throughputs. There's a reason why it took 20 seconds to build. So what we should do is we should throw that away. We should say, if it takes more than 5 seconds to build, I don't want it. I never want to use it. Throw it away. And that's great, except what about the people in Iran on modems, or the people in Cuba on modems, or the people in Zimbabwe on satellite phones over modems, or stuff like that? Those people, if we have a fixed 5-second timeout, then they're going to wait 5 seconds because that's how much it takes for them to get a packet onto the internet. And then it's going to say, ooh, 5 seconds, that's too much. I don't want that circuit. So what we really want is some sort of adaptive timeout where we look at how long it's taken you to build circuits in the past. And if your average is 10 seconds, then we cut it off after 15. And if your average is 2 seconds, then we cut it off after 5. And we're heading towards being able to do that. The next step is actually teaching the clients to collect their own data set of what circuit timeouts they've seen. And then we need to do the same sort of thing for stream timeouts. Right now, if I ask for Google.com, I'm going to ask one circuit, and if 10 seconds pass and I haven't gotten an answer, I haven't gotten any sort of response, then I say, well, I guess something went wrong with that circuit. I'm going to switch to a new one, and I'm going to have a new 10-second period for that. And if I get no answer there, I say, well, I don't want that circuit either. I'm going to switch to this and have a 15-second timeout. So we've got the same problem there, where we've got a fixed timeout that is both too long and too short. So even if the fellow in Iran is really patient and he really wants to get his Twitter out and he's willing to sit there for 10 minutes, his Tor is not willing to sit there for 10 minutes. His Tor says, oop, 15 seconds, clearly too long. So that's something that we really need to fix for people all around the world. Okay, and how much time do I have? Okay, sounds good. So there are a bunch of other things that we could talk about. We've been fixing performance problems with the Tor directory system a lot lately. So there are a bunch of things that the directory is supposed to provide. There are a bunch of different conflicting goals. One of them is we really want every client to learn all about the nodes in the network really fast. As soon as a relay shows up, we want all the clients to be able to use it. Because there are a lot of, especially in Germany and China, there are a lot of people on dynamic IP addresses, and that means every day you get a new IP address. So as soon as you've got a new IP address, it would be great to put you into the list so you can get used. At the same time, we really want every client to have exactly the same view of the network as every other client. Because if you're the only guy who knows about this new relay, and then somebody uses this new relay, it's pretty clear who it was. So we really need large anonymity sets so everybody gets to choose their paths based on the same information. And at the same time, we really want it to scale up to thousands of relays or tens of thousands of relays. So once upon a time, when we had no users, We just had the version 1 directory design. You put all of the descriptors for all the servers in one huge file, and everybody fetches that file every 10 minutes. And it's not that big because there are only 10 relays. That turned out not to scale for all sorts of reasons. So the much better design is we publish what's called a network status consensus, where we publish tiny little summaries of each relay, saying here's his IP address, here's a hash of the identity key, here's what ports he's listening on, here's the bandwidth value that you should use for weighting your choices. And our goal is to actually, so in the version 3 design, the stuff that's out right now, the one that your Tor client is using, there are 2 components to the directory. The first component is this network status consensus. And then the second component is all the descriptors. So you go out and you fetch your 150 kilobyte file, and then you fetch your 2 megabyte blob of descriptors. The next designs we're working on are throwing away that second component. There's no reason for you to fetch all of these huge descriptors with the keys and the exit policies and the contact information and so on. We should somehow figure out how to summarize that really compactly, either in the network status consensus, so every time you fetch a new consensus, you learn everything you need to know in order to pick paths, and in what we call a microdescriptor, which just has your long-term keys and your long-term exit policies and other stuff that won't change for a really long time. So I'd be happy to chat more about that later on if you're interested. So there are a couple of different results from this that we need to start pondering more. How do we figure out, for a given design, is it actually going to help things? Is it going to make things better or worse? Our current strategy is, let's think really, really, really hard, and then deploy it to 300,000 people, wait a year for everybody to upgrade, and see if we chose the correct strategy. That works okay, but it's kind of slow, and sometimes we're wrong. Wouldn't it be nice if we had a Tor network simulator? Wouldn't it be nice if somebody could actually simulate enough of the Tor protocol in order to figure out that if you raise this parameter, then everything's going to get faster, or no, you're wrong, it's all going to get slower. Doing measurements is a really good start. All the graphs that you've seen so far are from Karsten, and he's hopefully going to produce a lot more. We've got data. Archive.torproject.org will show you all of the directory information since 2004. It's something like 27 gigabytes. You can fetch it and do whatever computation you like. And then the last thing to think about, every time I'm working on making the Tor network faster, I'm thinking about how do I make it more efficient? How do I make the path selection less random? How do I make it more directly going from the user to the exit relay to the destination? And anonymity, in some sense, is the opposite of efficiency. So the more anonymous it is, the less efficient it is. And that's not a hard and fast rule. We need to figure out ways to get both efficiency and anonymity. But every time I'm messing with any of these things, I have to start saying, what am I going to do for breaking anonymity for the users? So it's really tricky. There are a lot of systems people out there who say, oh, you just build a network backplane that tells everybody everything that's going on, and then you can optimize it. And that's great if you're a systems person, but if you're trying to build an anonymity network, then you can't use most of the tricks that they have. So those are a bunch of different ideas. I'll be around for the next few days to chat about it more, and I think I've got a little bit of time for questions. Thank you. And I actually have a last slide here also, a bonus slide for the number of users that we saw over the course of June in both Iran and China. So we finally, just at the beginning of June, we rolled out our stats for how to safely learn about what's going on in the Tor network. And so we've got this baseline of 500 people a day in June until suddenly it spikes up to 8,000 people a day. And this was pretty cool results in terms of getting a lot of people to notice what's going on in Iran and a lot of people to realize that they need ways to get around their firewall. At the same time, China was doing its green dam thing during this period, and this was the point where they decided, hey, let's blot Google Search and Google Calendar and Gmail for 2 days. That'll show them. And it did show them. A lot of people in China started thinking, wait a minute, I thought my government was keeping me safe, but they can do that? I'm not sure I like this firewall thing anymore. So there's a lot more we can talk about censorship in an hour in that tent, I believe. Questions? We need a mic over
No?
here.
Oh, yeah, no.
There you go.
So we have 5 minutes. So any questions?
There are two people with hands up.
Just one question. There's been this court case in Holland against the Pirate Bay, where the judge is basically saying to the Pirate Bay they have to block IP addresses from the Netherlands, and it's not clear how it's going to work out and if they will have to comply and how they will comply and when. But theoretically that could mean that an enormous amount of Dutch users will start using Tor to access the Pirate Bay. What does that mean for the scalability of the system? If like 30, 40, 50,000 new users turn up in a relatively short period?
It means we need to get Tor faster, especially for people fetching small files. Because a lot of those people are only going to be fetching tiny files in order to bootstrap into the rest of their networks. So in theory, it wouldn't ruin the rest of the Tor network, in the same way that it would ruin the Tor network if a bunch of people actually started sharing files and doing file sharing and stuff over Tor. Where is the feedback coming from? Nobody knows? Okay, so in theory, it won't kill Tor. I mean, that isn't really what Tor was designed for. My goal with respect to all the people who want to dump lots of more traffic over Tor is how do we make Tor survive that while still being usable for the folks from Iran who want to do Twitter and people in the US who want to look at Amazon without getting put in their database and stuff like that. So our goal is to have all these different uses while surviving the people trying to overload it. That's how we kill the feedback. We turn off the mic.
How do you plan to deal with old clients and old relays? So if you've got all these new features, they might break if half the network is running old versions.
So the question is, how do we transition these things? How do we, yeah. For every single situation, we need to ask ourselves, first of all, is it going to be compatible if we roll out this new version at the same time as the old version? And then the worst question is the partitioning attack. If you can tell whether this user is upgraded, and not very many people have upgraded yet, then they're going to stand out. They're going to look different. You can attack them better. You can partition them out. So a lot of these things, we need to roll them out on the relays in a way that doesn't let you partition the users. If you're rolling them out on the clients, then perhaps the approach is we should give the clients the feature but not turn it on. And then 6 months later, when a lot of people have upgraded, then we flip the switch and suddenly all the clients get the new behavior. That also has the really useful feature that if we screw up, we can turn the switch back and then fix it and roll out a new one.
And we have 1 or 2 questions.
Yeah, I just wanted to put 2 things together that you mentioned. You said that you could have rate limiting in the client, but then people would just run a patched version to get the high speed. Also, you said maybe relays should have incentives. So why not just provide the patched version yourself to relays? I mean, you tick the box that says, I want to be a relay, and then you get rid of rate limiting. Would that work? Or rather, tell me why it wouldn't.
There are some anonymity systems out there that build their network by making people sign little statements saying, I won't be a bad person. And that sort of works policy-wise as long as you already trust everybody and you're in a small community. Part of the challenge with Tor is our anonymity comes from the diversity of relays out there. Once upon a time, Tor was just the people who found me at conferences and said, hey, Roger, you convinced me to run a Tor relay, I've signed up. But that scaled even less well than I thought it would. By the time we got to like 30 or 40 relays, I was getting mail from people in Moscow, people in Venezuela, people in Argentina, people in China, Japan, everywhere saying, I want to help out. And since our anonymity comes from the diversity of where these relays are, we can't say no to them. How am I going to make some guy in Moscow that I've never met sign a little thing saying, I promise to...
Yeah, I didn't mean to like sign anything. I just meant a tick box in the when you install, it says, I want to run a relay, so please remove the
Yep,
speed.
the honor system, where if you're a relay, then click here to get faster service. And maybe. I mean, we've got a lot of users out there right now who are trying to BitTorrent over Tor, even though we beg them not to. So, I mean, it really depends what sort of adversaries they have in mind, what sort of threat model they have in mind, how concerned they are for their own safety versus helping out other people around the world. Maybe, it might work. I don't know. It seems a bit risky, though.
And the very, very last one.
I just noticed in your statistics that there are exit nodes in China. Are they really make sense, and where do they come from? It's really strange.
So China is actually number 3 or number 4 by country in terms of providing exit relays. And what a fine question. It's also number 3 or number 4 by users. So I think a lot of the relays that we get are people who install Tor, and then they're looking through the dialogues and they find help save the world and they decide click save the world. I think that's roughly how our Chinese translation for make me a relay turns out to be. So I think there are a lot of people who press the button and then they set up new relays. A lot of them are at universities and they've got good bandwidth. So, I mean, in terms of where they're coming from, I think that's perfectly reasonable that there are lots of Tor clients who turn into relays. In terms of having exit relays in China, the next question that comes to mind, if I'm trying to look at BBC through Tor and I happen to pop out of China, it's blocked. I can't get it. So here I am in the Netherlands getting censored by the Chinese government. And I mean, it gets even messier than that. We found an exit relay in China that was doing SSL man-in-the-middle attacks on all its users. So if you pop out through that exit node, it takes off your SSL certificate for PayPal or whatever, and it puts on its own certificate for the province of whatever it was. So here I am in the Netherlands getting man-in-the-middle by the Chinese government. How do we deal with exit relays that are like that? On the one hand, the easy answer is, well, let's cut China out of the network. China's bad, everywhere else is good, and then we'll be safe. But that's not true. I mean, if I try to visit certain websites from Australia, I get censored by them. If I try to visit certain websites from Germany, I get censored by them. If I try to visit certain websites, I mean, the list goes on and on. Every country out there has its own list of things that you can't quite reach from those places. Gambling websites, you can't reach from the state of Minnesota at this point. They've enforced that on Verizon and Comcast and so on. So the bigger question is, the internet is not flat. You can look at it from different ways and see different things. And how do we handle that inside Tor? And that's a good lead in to the censorship panel, which will happen in an hour. Thank you.
So in around 5 minutes, we will stay on the privacy issue and we will hear a talk by Mike Brennan, 5 minutes or so.